In this video, I'd like to talk about depth-first search over tree data structures. So depth-first search is used for a couple different data structures aside from trees, but this video is going to be very specific to just tree data structures where there's this hierarchy associated with them. And because of that, it does make depth-first search a little bit easier to implement in some regards. So depth-first search is a traversal algorithm where it's going to be looking for specific elements. So this is a really great way to implement the questions of, does the number 2 exist in this tree? Is the word Bob in this tree? Or whatever else you want to do when you're searching for a specific element or searching for a set of data within a tree structure. So let's draw an example tree. And maybe for this example, I'll use a binary tree, but depth-first search works for trees of any shape and size. It doesn't really matter. This could be a binary tree like this. It could have a whole bunch of children under each node. It doesn't have to just be 2. It could work on sorted data and unsorted data. Depth-first search will traverse the entire tree looking for this thing. So, so here you go. Let's see. So 1, 2, 3, 4, 5. Let's add a couple more elements. 6, and let's say this has a couple more elements down here. 7 and 8. Okay, so the way that depth-first search traverses through the tree is it actually follows a very similar to an in-order traversal. And so if this tree were to be sorted, you would find that it hunts through the elements in the sorted order, which might be really convenient if you are working with a sorted tree. It might be one reason why you want to use depth-first search, because you're searching through the elements kind of in order. So if you remember with in-order traversal, it started by looking at our root node, and then it would look down here on the left node, the left child, and look at this 2. And then it would look down here at the 4, right? Because this is going to be the next one in order, right? Because remember that the 2 would be less than the 1, and then the 4 would be less than the 2, so on and so forth, right? So if this was in sorted order, that's sort of how we do our in-order traversal. Depth-first search behaves very similarly. And there's 2 ways to implement depth-first search that are common. One is iteratively, and it uses a data structure called a stack. And then the other one is recursively. So I'm going to talk about the iterative method that uses a stack data structure. Now, remember, a stack data structure sort of puts a bunch of elements into this collection, and you can add more elements into it, and then you can take elements off of it. And you can kind of think of a stack as a stack of pancakes where you're putting more pancakes on the top, and then you're eating the ones off the top. Or like a stack of plates at a buffet where you have this big stack, and as people come up, they take the top plate off. So there's 2 operations on our stack data structure. There's a push operation to put data onto it, and there's a pop operation to take stuff off. So if we look at our stack, and remember that stacks can be implemented using linked lists or using vectors. It really doesn't matter. The point is that you have this sort of collection that is maintaining elements that you can put onto it, and then you can remove elements sort of from the end or the top of this stack. So the way that conceptually depth-first search would work with this stack iteratively is it would start by taking the root node and putting it onto the stack. So we'd have the number 1 on our stack, right? And then that's when your loop would actually start. That's when your iteration would start happening. And your iteration is going to do a couple things. First is it's going to look at the next node that's on the stack. So in this case, it's going to remove 1 from the stack. So our node that we're currently looking at is node number 1. And this would be removed or popped from the stack. When we look at node number 1, it would add its 2 children, 2 and 3, onto the stack. And it's going to do this sort of in reverse order than you might assume, which you'll see why in a second. So depth-first search wants to explore down here the left side. It's going to traverse all the way down the left side of the tree first. So to do that, we want to make sure that 2 is actually on top of the stack, on top of number 3. So we're going to take number 3, and we're going to put that onto our stack. And then we're going to take number 2 and put that onto our stack. So we're putting the child nodes from right to left onto our stack data structure, right? In this case, with a binary tree, we'd put the right one on, and then we'd put the left one on. Now we'd go to the next iteration of our loop, and we would do the same exact process again. We'd say, what node are we going to iterate over now? Which one are we going to look at? It was previously we were looking at 1, and now we're going to pop the next one off the top of the stack. So we're no longer looking at 1. We are now going to be looking at 2. And 2 is going to be removed from the stack. It was just popped off. Now when we explore 2, we're going to add 5 and 4 onto it, right? So remember that we explored 1, and now we're exploring 2. And now we're going to add 5 and then 4 onto our stack. And then we're going to do the exact same iteration again. Okay, well, let's pop the next one off and explore that one. So we're going to pop 4 off, and that is going to be the node that we are now looking at, 4, right? So we explored 1, 2, 4. And then 4 is going to add its right and left child nodes on. Now 4 doesn't have any, so there's nothing to add onto this data structure. So we go to the next loop, or the next iteration, right? And it pops the next thing off, 5. And you may already see how this is sort of doing this sort of in-order traversal in the same way as our in-order traversal function did. So we look at number 5, and that's going to be the new node that we are currently looking at. 5 adds its children, the right and the left, and there's nothing here to add, so we don't add anything else onto our stack. And then we pop off the 3, right? So we explored 4, then 5. And now we're going to explore the node 3, right? So notice how it traversed down the right side of this tree, then explored 5. And now that it's already explored this entire section of the tree, it's going to go back here and start traversing 3. And it's going to continue in the same manner, traversing 3 down to the 6. Then the 6 is going to add the 8 and the 7 on. It's going to look at the 7 first, and then finally look at the 8. So you'll see that this sort of operates in the exact same way as our in-order traversal. And in fact, in-order traversal can be implemented using a stack data structure like this as well. So if you're interested in the recursive method of the depth first search algorithm, you could go look at how we talked about doing the in-order traversal. So what does the pseudocode for this thing kind of look like? Well, we have to do a couple things. We need a stack, right? So let's call this thing S, right? And this is our stack of, or actually maybe we'll use a better variable name than that. We'll call that next nodes. So we have this stack called next nodes. Now actually in code, this could be as simple as a vector, and you're just adding nodes onto the end of a vector, or a linked list, and you're adding nodes onto the end of a list, and then you're removing them from the end of the linked list or removing them from the vector. Or you could create your own custom stack data structure, or use your custom stack data structure where you actually have a push and a pop function within it, right? But for the sake of the pseudocode, you can imagine that when I say we are pushing something onto next nodes, it means that I'm adding something onto the stack, and when I pop something off of next nodes, it means I'm removing something from the stack. So we need the stack of next nodes, and then we need a node that we are currently exploring, and I'm going to call that n, just a lowercase n, like I did in my example up here, right? So n was the node that I was currently exploring. I started off at 1 at my root node, and then sort of traversed through the tree. Then the first thing we're going to do is we are going to add the root node onto the next node stacks. So we need to do something like this. Next nodes dot push, which means that we're just adding it onto this list of next nodes, and we're going to add the root node onto it. So then we're going to have our main iterative loop. So our loop is going to loop while, actually I'll change that into a while loop. So we're going to say this thing needs to continue looping until next nodes is empty, until there's no nodes left to explore. So we're going to have something that looks like this. Well, next nodes is not empty. And we're going to do this code underneath it. We are first going to pop the next element off of next nodes. So we're going to say n is equal to right? Take the next node off the top of, take the next node off the top of our stack and set that equal to n. Then we are going to say next nodes dot push n dot right. So the right child, and remember this is just for a binary tree. You would need to expand this a little bit if there were more child nodes, more than just a right and a left, right? You'd want to add all of the child nodes of the node onto it. But we're going to add the right node, and then we're going to add the left node. So we say next node dot push left, right? Now I know this is pseudocode, but I'm kind of using sort of this pointer operator, right, that we'd see in like C++. And this is essentially the entire fundamentals of our depth first search, right? We are looking at the next node, we add the right and the left, and then it goes back up here while there's still data on our next nodes, which we know there will be because we just added right and left onto it. It's going to look at the next one, and in this process, it's going to remove it and set it n equal to it, and then it's going to add the right and left, and then it's going to look through this, right? Now, finally, we need that element of like, we're actually searching for something. So right now we're just doing this traversal. To actually search for something, well, we need to check the value of n. So we need to add something in here. We'd probably say something like, well, if n value is equal to whatever we're searching for, right? X. If we're searching for the value x, then we can return true. And that's it, right? As we're searching, every single n that we look at, if we find the value that we're searching for, then we return true. And then if we get to the end of our while loop down here and we say, you know, hey, we never found it, then we would return false. And there you go. This is the entirety of the pseudocode for a tree depth first search.